Okay, the suggested questions. First set, page 561, numbers 1 to 4. So here are our equations. 1, 2, 3, 4, 5 of them. We have two constants. C equals 2.9979 times 10 to the 8th. And of course, Planck's constant. H equals 6.626 to the negative 34. And this one is joules seconds, this one is meters per second. So number 1 says the stopping potential to prevent current through a photocell is 3.2 volts. Stopping potential, that's VO. So VO is 3.2 volts. And the question wants to know, calculate the kinetic energy in joules of the photoelectrons as they are emitted. So you're looking for EK max, really. And we know that VO is equal to EK max over Q. So EK max is just equal to Q times VO. So EK max is equal to Q is an electron, 1.602 to the negative 19 coulombs, and V is 3.2 volts. Now, before you ask, I left off the negative because remember, energy is a scalar, so we don't need to worry about directions here. The negative would just mean that the field wanted to do the work instead of you having to work on it. So when you multiply these together, you get an EK max of 5.1264, and there's other digits, times 10 to the negative 19, and that is joules. So number 1. Number 2, stopping potential for a photoelectric cell is 5.7. So number 2, VO is 5.7 volts. Calculate the kinetic energy in electron volts if the photoelectrons emitted. So again, VO is equal to EK max over Q. So EK max is equal to Q times VO. Now, if they want it in photoelectrons, instead of putting your charge in coulombs, put your charge in electrons. So it's 1 electron times 5.7 volts. And lo and behold, you get an EK max of 5.7 electron volts. Now, if you would want it, you could put this in as 1.602 and get your joules, and then divide it by the 1.602 and get back the 5.7. So if it's something this simple and they're asking you for it in electron volts, instead of putting your charge in as the charge on one electron in coulombs, put it in terms of electrons. It's just 1e, one elementary charge, 1 times 5.7, pretty easy to do in your head. Number 3 says, the threshold wavelength of sync is 310 nanometers. Wavelength, lambda, threshold, so it has to have an O. And it's 310 nanometers, or 310 times 10 to the negative 9. So from that we can find the threshold frequency, because we know C is equal to F lambda. And so C should be equal to FO lambda O. So threshold frequency should be equal to C divided by lambda O. So 2.9979 times 10 to the 8th meters per second divided by 310 to the negative 9 meters, or 3.1 to the negative 7. And when you do this, you get an FO of 9.6706 times 10 to the negative 9 hertz. Okay, that's part A. Part B says, what is the work function? Well, then WO is just equal to HFO. So WO is equal to 6.626 to the negative 34 joules seconds times that 9.6706 to the negative 19 hertz. Oops. And when you do this, you get a WO of something in joules, which I already turned to electron volts. I just need to write this number down. It's 3.999856 electron volts. Oops. So 6.626 to the negative 34 times 9.6706. This is now rounded to the negative 19. 6.4077, etc. to the negative 19. And then when you multiply by 1.602 times 10 to the negative 19 joules per electron volt, you get 3.999399856 electron volts. And then the C says zinc in a photocell is irradiated, so light is shone on it, ultraviolet light, 240 nanometers. So now in part C, they're telling us the wavelength of the light is 240 nanometers. So we can find the frequency of the light, C divided by lambda, 2.9979 to the to the eighth, not negative. Light's moving quite fast, not slow. Divided by 240 to the negative 9 meters. So we get our F, which I believe is 1.249125 to the 15th hertz. And so if we keep reading the question, it says, what is the kinetic energy? So now we're looking for EK max, and that's equal to HF minus WO. And it wants to know the kinetic energy in electron volts. So EK max is equal to 6.626 to the negative 34 joules times that 1.249125 to the 15th hertz. And then we're going to subtract the 3.999856 electron volts from it eventually. So first step is to do this first term, and it's going to be in joules. So 6.626 to the negative 34, and our joules are going to be 8.2767 to the negative 19. But we can't subtract electron volts from that, so then you need to switch it to electron volts by dividing by 1.602 to the negative 19. And when you do, this first term becomes 5.16648 electron volts. And from that, you're going to take 3.99856, which is pretty close to 4. 1 minus 3.9929, 399,856, and you get 1.16 electron volts. Okay? So that's number 3. Number 4 says the work function for cesium is 1.96 electron volts. So WO 1.96 electron volts. Find the threshold wavelength. So WO is equal to HFO. We need FO. So WO over H. 1.96 electron volts divided by 6.626 to the negative 34 joules seconds. Hopefully you realize, wait, I can't divide these. This is electron volts, this is joules. I need to switch this to joules, so multiply by 1.602 to the negative 19 joules per electron volt, and then get my FO. So